thank you very much for coming and for helping in the organization.
Well, Tommaso, I have to say that you did all the work. So I'm glad that, thanks for saying this. We've been co-organizing this with the last one 2 years ago in Darmstadt, or actually Seeheim, and I see many faces that I saw 2 years ago. So that's good. Yes. And then I think this is a very successful series, and we're more than happy to contribute here.
Okay, and I would also like personally to thank a lot all the administration of our department that had supported the organization of the event, in particular Mr. Edo Mazzi, who took care of many of your registrations. So big thank to him. A couple of recommendations before to start. First of all, every speaker to stay in 25 minutes. Please stay on time. Use 20 minutes for presentation. Leave space for question compared to many other meetings and conference. This is a conference where discussion is very important. So please ask as much as you can, because discussion is very important to, let's say, go on with all the developments and so on. If you need Wi-Fi access, here you can find the password and login. So who needs it, just take a piece of paper. If you need an adapter for your PC to plug it, here it is. The last row, this right row on your right, of course, on my left, is without plugs. So in this row you can plug your PC. And I think that with this we can start the conference. Unfortunately, the first speaker is not here, so we can start immediately with Gabriela Braccio from University of Valencia. I think you can sit here. How can you?
I prefer to stand.
You prefer to stand? You can stand here if you want.
Yes.
Or I don't know if there is a. Okay, you do this. Perfect. Okay, so you can do whatever you want in this case. Need a microphone?
No, this is on. Well, this is on.
Yes, this is on. Okay, so. Okay, title of Gabriela's presentation is Numerical Investigation of the Combustion Behavior in a Compression Ignition Oxy-fuel Engine fueled with OME-free for pollutant emission reduction.
Okay, so thank you, Tommaso, for the introduction. Good morning. Do you hear me fine? Yes, so I am Gabriela Braccio from CMT at Universitat Politécnica de Valencia, and I am going to present the work entitled Numerical Investigation of the Combustion Behavior in a Compression Ignition Oxy-fuel Engine fueled with oxymethyl ether for pollutant emission reductions. Well, this work has been done in collaboration with my colleague, Professor Ricardo Novella and Casio Sport Fernandez, also from CMT, and with the strong collaboration from Professor Tommaso Lucchini from Politecnico di Milano. The content of the presentation is the following. So I will start, of course, with an introduction. In the second point, I will describe the objective, followed by the methodology. And in the 4 points, I will discuss the results. I will be focused on the oxy-fuel engine behavior or performance when this is fueled with oxymethyl ether. Then we are going to analyze the sensitivity regarding the number of orifices in the injector. And finally, I will present the outcome or the final configuration that we are going to manufacture. Finally, some conclusions and future works. So starting, of course, with the introduction, all of us that we are here, we are working strongly on the development of new systems to reduce the pollutant emissions. And in this case, we have like 2 alternatives or different alternatives. And in this spectrum from alternative, we are focusing in one side in the fuels, alternative fuels, and also we can develop new combustion models. In the first side, we have different options as well, but now we have paying a lot of attention to the e-fuels for compression ignition engines. In this case, we know that those are very good for improving emissions, specifically reducing soot particles, and also that the actual engines can be used without some big modifications. The drawback, let's say, apart from the broadband availability of these fuels, is that the low heating value is lower than the traditional fuels. It's about the half of the low heating value of a conventional diesel. Well, on the other side, regarding the combustion concepts, there are also different technologies that we are trying to analyze, for example, RCCI, HCCI, etc. And in our group, we are developing since 3 to 4 years ago something that is called oxy-fuel concept. Okay, so in this case, what we are doing is just to remove the nitrogen from the air. So in that sense, we only introduce in the engine oxygen, okay? We remove the nitrogen and we are introducing the oxygen. Well, if we introduce only the oxygen, the temperature in the combustion is quite high. So just to control the temperature in the system, we need to dilute this gas with EGR. So we are introducing the gas which is made or composed by CO2 and water. Well, if we remove the nitrogen, the good thing, the advantage is that all the products that are formed with nitrogen are also avoided. So we are not going to have NOx. Well, here, this is the main advantage, but the problem that we have is that the efficiency or the fuel consumption is quite high. It decreases the efficiency, so we need to consume more fuel. Well, in the last edition of this conference, we presented a very deep analysis of an engine using oxymethyl ether and another analysis of an engine fueled with standard diesel in the oxy-combustion conditions. But in this case, what we want to do is just to see how is the performance when we combine this, an engine of oxy fuel concept and fueled with oxymethyl ether. So for that, we need to develop a platform, of course, CFD platform based in OpenFOAM using the device. And well, here is to evaluate the performance of these two concepts, oxy-combustion, fuel with oxymethyl ether. To evaluate this new concept, we just propose 3 partial objectives. So the first one is the development and validation of the engine model using OpenFOAM. So for this, we are using the conventional fuel because we know a lot about this. So it's a good point for validation. Then in the second partial objective, we are doing an assessment of the influence of the comburant on the combustion performance. Well, in this case, the comburant chosen has been oxymethyl ether number 3. And then in the last partial objective is the analysis of the effect of the oxidant composition on the combustion and pollutant formation. Well, to achieve these 3 partial objectives, we need to fulfill or accomplish, let's say, some requirements, especially regarding the flexibility. Okay, so we need to have a platform that is able to be flexible with the geometry of the piston, the definition of the nozzle holes, the definition of the setting conditions in terms of injection parameters, and also in terms of the gas management. And of course, since we are changing the fuel and the gas composition, should be flexible in that perspective. Well, to achieve, let's say, this objective, we propose a methodology based on 5 steps. The first step is the very basic one, so to do the preparation of the model in CFD. And this is done using a diesel compression ignition engine with a compression ratio of 16. And once this is validated, we move towards the second step and fuel the same engine, but using oxymethyl ether, with the same engine, with the same compression ratio. In this case, we want to evaluate how is the potential for the soot reduction. In the third step, we move now to the oxy combustion concept, and here we are targeting to the NOx reduction, okay? Well, we knew from the previous analysis that we have been done for the 3 last years that we had to increase the compression ratio up to 20 to make this work properly. Well, once we have this developed, then we wanted to see how is the sensitivity to the number of orifices in the injector with the aim to improving or to recover the efficiency that we lost when we apply the oxy-fuel combustion concept. And then finally to decide which is the best configuration. Well, let's go to the first step. So in the first step, we just prepare our model using the OpenFOAM device. In this case, we were modeling the closed cycle. So it means from IBC to exhaust valve opening. And we use the fuel N-octane. And well, in this case, the models that we use for the platform is the KHRT for the breakup, also the RNG K epsilon for the turbulence. We also use the RIF for combustion model, and Spalding for evaporation, and Engelberger for the wall heat transfer. Well, we are here modeling only one sector of the engine, just taking advantage of the axisymmetry of the system. In this case, we were using a nozzle with 10 holes. So that means that we are dividing the combustion chamber in 1/10 of the domain just to speed up the simulations and save resources. The engine that we are using is just a compression ratio of 16, as I already mentioned before, with the 10 holes, and the diameter is about 112 micrometers. Well, here we also have an example of the mesh. For that, we use the tool developed here at Polimi, the DCC mesh generator, which is quite handy for us. And we just develop a tool to parameterize all the piston and the bore, etc. Okay, so then if we need to change the diameter or the size or the shape, it could be done automatically. Well, we represented here the full load conditions. However, we did the validation also for other partial loads. However, here in my results, I will present only the full load operating conditions for sake of brevity. Well, so just in terms of the results, we just did the very first step was to do the sensitivity analysis of the mesh. So we tested 5 meshes, and we just realized that after the 3rd mesh, we found a convergence or independence in the mesh resolution. So we just took the 3rd mesh, which is the one with the lowest number of cells compared to the 4th and the 6th. And in this case, one closed cycle took about 16 to 18 hours, okay? Well, when we compare or validate the pressure, so we found a really nice agreement, okay, in the pressure trace. So here we are comparing the experiments in the black line and also the simulations in the blue line, and also compared to the rate of heat release was fair enough, okay? So we were happy with these results, and also compared to the IMEP was very good agreement. We also validated the number of the consumption and the emissions, NOx, and also the sweep behavior. So at this point, we said, well, this model is fair enough. It is prepared, and let's go to the second step. In the second step, what we did was to change the fuel characteristics. So we are not using diesel anymore. We are using oxymethyl. Well, to use the oxymethyl, we have like different options in the market. Let's say the most popular is based on a mixture of oxymethyl 1, 2, 3, 4, and 5. But after some analysis that we did, we saw that it's easier or more simple to use only one of them. And we chose number 3 because it's representative of all the mixture. Okay, 3 and 4, but then 3 is also a good sample. Okay. Well, we use exactly the same engine with the same mesh, the same profile, the same boundary conditions, same geometry, compression ratio, etc. because it was well validated. And the thing that we updated was the fuel, of course, because here we have different properties, especially bigger or higher density values, different viscosity, also different boiling point, etc. The most important here is the lower heating value. So we had to adapt this heating value because it's almost the half. So we need to increase the fuel quantity, the fuel amount, okay, just to compensate and to get the same energy that we were obtaining when we introduced the diesel, okay? We also wanted to have or to obtain the same indicated mean pressure. So for that, we adapted the rate of injection profile. This is the only thing that we modified beyond the fuel properties, of course, in all the libraries and the mechanism, which were coming from Cayetal, that here we have the reference. So to adapt the rate of injection measurement, we have an internal tool, which is called virtual injector model. This is the diesel one, and here you see that we are injecting more fuel quantity to achieve this higher energy, or the same energy because of the low heating value of the fuel. Also, we had to increase a little bit the duration of the injection just to achieve the similar IMEP value. Well, to do this, we kept the same number of orifices, and we also kept the same injection pressure. So that means that we had to increase the diameter of the nozzles, okay, to achieve this greater profile. If we go to the results about this oxymethyl evaluation, well, we can see that here we are comparing the diesel and the oxymethyl both from CFD. So we have, well, although we are introducing another fuel, the engine is behaving fine because the pressure is more or less similar, well, because we were targeting the same IMEP, okay? And in terms of the combustion behavior, we see interesting things. The first is that we have a slightly sooner start of combustion. This is typically, we have a different cetane number, and well, we expected to have this. Also, we have a higher rate of release, of energy released. And then we also see a faster burnout, although the rate of injection is longer, okay? But this is also characteristic of this type of fuels. This is in accordance to what we have seen in other experimental results that have been done in our department, and also in accordance with the literature. Well, if we go to the emissions evaluation, we compare the soot and we see that there is almost no soot. So here we have the diesel, which is the blue, and the red one, it's really hard to see because the scale is quite little, okay? So we are obtaining what also the literature represents, and this is what we were targeting. However, if we go to the other emission that we are evaluating, which is the NOx, we saw here that the OMEX has a greater value. Here we have the diesel, the reference from the previous engine, or the same engine with the previous fuel, and then we are increasing almost double the quantity of the NOx, okay? Well, we also expected this. And 2 years ago, when we came here, we presented like an optimization tool to use this type of fuel, or very similar to this one, but to decrease this value of NOx. Well, beyond this, of course, the positive is that we are decreasing the soot. The negative is that we are increasing the NOx, but also here we were obtaining a slightly lower efficiency in the engine and a slightly higher fuel consumption. Well, just to, I would like to point out that this fuel consumption is just normalized by the difference of the low heating values, just to make a fair comparison, because there is a huge difference between the heating value of the fuels. Well, so at this point, we said, yes, we are happy, but we want to improve this even more. So we thought, let's use the oxy-fuel engine that we also have developed in our group and try to combine both, just to get rid, or just to evaluate if we can get rid of this oxy-fuel, or of this NOx, okay? So, well, we just came to our engine based in our department. In this case, as I just mentioned, here we are removing the nitrogen. We are using a standard, let's say, conventional compression ignition engine coupled with a huge heat recovery system that we present here. But for us in the combustion side, let's say, the important thing is like the input conditions that we are going to have in the combustion chamber and the requirements that we need to fulfill to deliver the gas in the exhaust, okay? So, well, this is a work that we have been applying or doing for, as I said, 3 years, 4 years, combining 1D and 3D simulations, okay? Well, after this big, let's say, or long research term, we have came to the thing or to the conclusion that to make this work properly, we need to increase the compression ratio from 16 to 20, okay? This is because in the intake, we don't have nitrogen, we have just a gas mixture from O2, CO2, and water. The composition of the properties of this composition are different. So we need to increase the compression ratio to overcome the problems of that composition. We also adapted the injection configuration to be able to work with this higher compression ratio. This was obtained after, let's say, 1,000 simulations combined with optimization algorithm that we presented 2 years ago, which is called particle swarm optimization. Well, after this, we have again increased the compression ratio. We also increased the injection pressure, and we changed the composition. These values of oxygen, water, and CO2 are coming from our 1D tool. Also, after different evaluations. Well, the mesh that we obtained here, as you can see, is an oriented mesh. Well, now what we did later was to include here the oxymethyl ether fuel, because all the previous tasks for the oxy-fuel concept was done only with diesel. But in this case, we just plug the oxymethyl ether mechanism and fuel library. Well, and here where we present the results directly regarding the pressure trace. Okay, so in red, we have the air with oxymethyl ether, the one that we have characterized before, and in yellow, the new condition with oxymethyl ether plus oxycombustion. Well, we see that here we have a lower pressure value. This is because of the composition, as I mentioned. And then here the adiabatic expansion coefficient, the gamma, is lower. So we expected that during the compression stroke, we achieve lower pressure value. Well, however, the combustion, when we evaluate this, is working more or less fine. We see that the ignition starts more or less in the same point. To do this, we had to advance 1 degree the injection here, because when we are doing the injection of the fuel arrives into chamber conditions with lower pressure and lower temperature. So the delay is a little bit longer for the ignition itself. Well, so here what the main difference that we have seen is that we have higher rate of combustion. Here you see the yellow one, and then that is finishes sooner. Well, this was behaving more or less properly, but we just found that the efficiency was lower compared to the OMEX with air. We expected this because we are having a lower gamma, and by definition, thermodynamically, you will have lower efficiency. But also we have a huge consumption here. We are not burning all the fuel. So we need to find a way to improve this performance. If we evaluate the pollutant emissions, Well, what we realized is that the NOx, of course, here is 0 because we don't have nitrogen in the gas composition. So it's virtually 0. So here is the initial case from oxymethyl. Also, if we evaluate the soot, here we see some traces, but this is quite little, okay? Pay attention to the magnitude, so it's quite little. However, when we evaluate in the oxy-fuel combustion mode, it's even lower. So these and these are advantages. The problem here is that we had higher CO values, which is related to the lower combustion efficiency. We are not burning all the fuel that we have there. So to understand what was happening there, we just let's analyze where is the fuel going here. So we analyze some slides. Here in the upper row, we have in the air an oxymethyl, and in the intermediate, we have oxy operation mode. And what we can see is that in the initial one, what was working properly or fine, the fuel is maintained here within the bowl, just slightly here in the step region. But in the oxy-combustion mode, we have a lot of quantity here in the squish region. There is not enough room for the fuel in the combustion chamber. Okay, so that means that there is some kind of fuel that is here that is not able to find the oxygen and to burn properly. Also, when in the last row, we present just as a comparison purposes, the oxy and the diesel. Well, here, this problem that we are facing here in the oxy combustion is because we have a higher compression ratio. So we have lower volume. So in the combustion chamber, then the system or the fuel needs to go towards this part. If we go to the evaluation of the acetylene here, we also wanted to understand how it is going on. So here we have the air plus Omex, and then here again the oxy plus oxymethyl. So well, here we see that although this is like a low soot fuel, we have some formation of acetylene and with considerable values at some point, but it is consumed. Most of it is consumed after the end of the combustion phase. Just as a reference, we present here the oxy with diesel, with the standard diesel, where the acetylene values are considerably much higher, okay? So, well, this is a good thing of the oxymethyl, and our combustion model is able to predict and reproduce this. Yes, and as the last result, evaluating the concept, we present the feed temperature diagrams just to see how is the evolution globally and just in accordance to what we presented with the acetylene. So in the first plot, we have the air plus oxymethyl, and then we see here for different Crank angle degree from 0 and to 4 up to 40. And well, there is some part of the fuel or yes, of the mixture that is in the Sud Peninsula, but this is quite smaller compared to the one that we would have if we are injecting diesel. Okay, so well, this is also what has been registered by other people in the literature, other researchers. And then here we see that we have some mixture in the NOx Peninsula. We are achieving higher temperatures, and this is what we also saw in the results in the NOx trend. If we just compare this with the oxy-fuel combustion, we see that we are achieving lower fees, so we are avoiding even more the soot region, and in the crank angle at the end of the combustion, this is even lower. Regarding the NOx, however, it is depicted there, we have no nitrogen. So although we are having higher temperature in the combustion, we are not producing nitrogen, NOx, because we don't have nitrogen there. Also compare here with what we have in the standard conventional diesel. Okay, so well, this is quite fine. We are not producing soot, we are not producing NOx, but the combustion efficiency was deteriorated. Okay, so we needed to find a way to recover this combustion efficiency. So well, we said, let's go to the easy because we have done considerable modifications in terms of the combustion chamber, etc. And just only focus on the number of holes that we are going to put in the injector, okay? So we did a sensitivity of this number of holes, maintaining the same mass of injected fuel. So that means that we had to decrease the diameter of the nozzles. Well, we know that if we increase the diameter, of course, we are going to decrease the droplet size, improve the mixing, evaporation, etc. And we expect that the burn rate is going to be better. But also, we are going to avoid that part of the fuel goes to the squish zone where we were having the problems of the airborne fuel. So, well, here is just a final result comparing the sensitivity of the fuels. I know that here we have a lot of plots, okay, a lot of curves. All of them are just comparing the 7, 8, and 9 holes configuration. We have availability of this, all these nozzles in our experimental facility as well. And then also with the OC diesel, which is the reference case, and the air with only Omex. And well, here maybe it's hard to see, but with the 9 holes, we see an improvement in the combustion performance, which is here the gray line. Also, if we compare the pressure, well, this is just the pressure, all these with the low value, of course, are in OXY configuration. We increased a little bit the IMEP, okay? But the most important thing here is that when we compare the cumulative heat release normalized by the total fuel injected with the 9 orifices, we are recovering and targeting the red one, which is the air plus Omex, which is the target, okay? Well, so with this, we just found that what we wanted here, we are just comparing in this short example of the video where we are represented the acetylene, just as the reference with diesel where we have a lot of red, so it means high intensity of acetylene. Then here we see more blue regions, but when we go to the 9 holes, which is the new thing, we have less formation here in the squish region, so we are improving the system with this strategy. So at the end, this is the one that we selected for manufacturing and testing in the engine. Just as a final comment, this is an overall analysis of the influence or the sensitivity regarding the injection size diameter. So here we are presenting the HC. So we have less unborn hydrocarbons with the 9 holes. So it's good. We are increasing the combustion efficiency and they are related, okay? And this is what we were targeting. So again, the best configuration is this one. If we are increasing this, we are increasing the gross indicating efficiency as well. Well, so with this, I finish the presentation. So just as a summary, we have been able to combine the both platforms that we have developed before, one for the oxymethylator and the other one for the oxycombustion. And well, the good thing is that we were able to decrease the NOx, we are able to decrease the soot. Of course, we are sacrificing a little bit the efficiency and the fuel consumption. Okay, so there is still room to improve. Well, as a next step, we need to validate these results with experimental data, and the test bed is, let's say, already in place. Let's wait the results so we can completely see if these trends are well captured or if we need to readjust some. Also, we need to explore more or other operating conditions. And yes, we need to right now, what we are targeting is to analyze other fuels. This is just, let's say, in another work package for another project. So we want to see the spray development using, for example, ammonia. And just as a sneak peek, because this is like the next step, but this is just ongoing right now, also together with the support from Professor Tommaso. So here we are just comparing our experiments in the injection of ammonia with some CFD simulations using the OpenFOAM tool. Okay, so right now what we are just comparing is the liquid length and also the evolution of the vapor penetration. While this is high pressure liquid ammonia, we are injecting here at 600 bar, more or less. Well, more or less, no, 600 bar, and at non-reacting conditions. And the next step is just to move towards the reacting case. And then, of course, move towards the engine. So I just would like to finish just saying thanks to our funding in the Generalitat Valenciana and funding from the national government of Spain, and of course to all the Polyme team, especially to Professor Tommaso. Thank you for your attention, and yes.
Thank you, Gabriela, very much for your presentation. Any question from the audience? Yes, please.
A short question. So is nitrogen by
Okay, we replace all the nitrogen using CO2 plus water. And we increase a little the O2 concentration.
Okay, so when you calculate the thermal efficiency, I think 35% is 23. Do you take into account the fact that you have nitrogen, or was indicated?
No, it's indicated.
Okay.
Yes.
Okay.
We have time for another question. Yes, please.
At some point you showed this one. You see that as well. Again, is faster than.
Yes, we think that is because of the reactivity of the fuel. We have more oxygen. It is more reactive, and it also burns faster.
Do you think it's the end CO2 conversion levels to the reactor, or from diesel to CO?
Is this diesel?
Well, sometimes you may think that at the end, what is close happens CO to CO2. That reason, just more oxygen, or is it still CO?
Well, I cannot ensure if this is C oxygen to CO, but yes, could be.
Yes, please.
Yeah, thanks for. Could you tell us a little more details about your suit model you implemented? I understand it cannot be the most complicated one, but at least just to be able to predict the difference associated with different types of fuels, especially considering the high pressure operation. There's a lot of unknown challenges about keeping the right pressure scaling of the sensitivity. So did you make some extra effort to prove the prediction?
No, we are just using the suit model, yes, the standard one.
What's the main food precursor in the model? The main species that leads to the cellulose.
Well, we are using the standard suit model, so yes, it's the question.
It's the.
I was just wondering if you need to do a little bit more adjustment and validation.
Actually, we haven't done when we are using the device and the RIF and all the models that we have there. We didn't do a lot of tuning regarding the suit model, and we predicted properly. Yes, and when we're using the diesel, and also for different operating conditions, it was working quite fine. Yes, also compared with other models that in other platforms that we have used also, in that one, maybe we had to tune a little bit. But in this case, for the OpenFOAM and RIF, we didn't, no, we used it as it is.
Okay, so thank you very much, Gabriela.
Okay.
And, I think we have one. Okay. Chiudo poi la porta perché non ci si carezza.
No.
Okay, so next presentation is from Lorenzo Sforza from Politecnico di Milano. Title is Modeling of Hydrogen Fuel Spark Ignition Engines for Light Duty Application. Please.
Well, thanks, Tommaso, for your kind introduction. Ladies and gentlemen, good morning. First of all, I would like to thank all Polimi people that actively contributed to the material that I will present today in this talk. And as well, I would like to thank also our academic and industrial partners that allow to carry on this research thanks to sharing many experimental data. So first, we will have a look together quickly at the background and the motivation of the research that I will present, and then we'll go into details of 3 different engine configurations, in particular spark ignition engines fueled with hydrogen. The first, it is a direct injection configuration, the Sandias optical hydrogen engines, also called SOFI. Then we will have a look together at 2 port fuel injection configurations. The first is the Valencia Penrose configuration, also called with the acronym PENNY, and the Dumarace flathead engine can we call FLY engine for simplicity reasons. So nowadays, internal combustion engines are experiencing a disruptive evolution in order to meet the main target of carbon abatement. And to reach this target, there are 2 ways mainly. So first, the usage of alternative fuels, zero carbon or low carbon ones. And the other one is the usage of a new engine concept to maximize the engine efficiency. So in this talk, we will focus on the hydrogen engine concept as a solution to decarbonize the power technology. Hydrogen is a non-conventional fuel if compared to traditional hydrocarbons, and so we need to assess our consolidated CFD methodologies prior to applying these methodologies for this engine design. So first, let's have a look at the direct injection hydrogen engine configuration called SOFI. So this is a Penrose configuration with a single hole injector and a flat piston. In this case, we studied a non-reacting condition where hydrogen is directly injected in pure nitrogen. Here we have, in this condition, no tumble, basically, and the hydrogen injection is carried out completely during the compression stroke. So about the numerical approach, we simulated only the power cycle by using a RANS methodology, and as a first step, we employed for turbulence model the standard K epsilon 1. At intake valve closure, we initialize the flow at rest, and pressure and temperature are provided from experimental measurements. About the hydrogen injector, we extruded 20 millimeters of mesh starting from the nozzle exit section in order to avoid interactions between the hydrogen inlet section and the flow dynamics that happens at the nozzle exit, like expansion fans or normal shocks that are expected in case of an underexpanded nozzle. And in this case, at the inlet, we apply mass flow rate and the total temperature. About the mesh, in this case, we studied two different mesh types. First, we started from a base configuration where we have only a half engine domain because of symmetrical reason. The mesh is non-oriented, hexaedral nominal topology, and the piston motion is accomplished by means of the dynamical addition removal of layers. Then we compare this base mesh with a refined strategy where three conical refinements are applied at the exit of the nozzle. And this importance of applying these refinements is identified by these results, where if we look at a certain instant during the injection process and we look at the Mach number, we can notice that with the base mesh, we are not able to predict the flow structures in terms of expansion fan and normal shocks, while the refined approach is able to reproduce these phenomena that impacts on the distribution of the hydrogen inside the cylinder. In fact, here, if we look at the molar fraction distribution with the refined mesh, base mesh, and experimental, if we move from right to left, and we look at the instant immediately after the end of the injection process, we can observe an improvement of the results with the refined mesh because we are able to predict a reduction of the jet momentum due to the resolved normal shocks. So it is important with hydrogen to have an enough mesh refinement to properly capture such events. However, if we look far away from the end of injection during the compression stroke about the hydrogen mixing to nitrogen, we still have some underestimations, but compared to literature, these results are for now satisfactory. These good results for the mesh can be also detected if we look at the velocity distribution that in the same bottom region, where with the refined mesh, we were able to improve the numerical experimental agreement. Now let's move to the port fuel injection configuration of the Penny engine. Penny engine is a Pentroff engine with a central spark plug and a shaped piston. And in this case, we have a rather high tumble ratio, and we studied ultra-lean combustion by means of variation of load and an increasing of dilution. Here, again, mesh features are similar to the SOFI engine. Basically, again, a half domain of the engine because of symmetrical features and non-oriented mesh. Piston motion, again, with dynamic addition removal of layers, and on homogeneous mesh features. But to study this configuration, we tried to use a, let's call, fast 1D 3D approach. This approach that we developed here at Politecnico aims to have a quick study of an engine configuration without performing long gas exchange 3D simulation, but providing a first assessment of the engine. So to do this, first, you need to study the engine with a 1D approach. In this case, we used GasDeal software, which is our in-house tool to do these simulations, considering the full engine schematic. And then we retrieved integral closure condition of pressure and temperature inside the cylinder to initialize that 3D simulation performed with Libais, which is software developed here at Polimi based on the OpenFOAM technology to study engines in order here to simulate only the power stroke. Then, obviously, after the compression, we were able to simulate combustion. But at the interval closure, we need to initialize the tumble if we do not have a complete gas exchange simulation. And to do this, we developed a new simplified strategy that consists into 3 steps. So first, we initialize the tumble by providing a tumble ratio which is defined by the user. The user also can define some shape function for the tumble along its axis and its radius. Then we let adapt the flow to the geometrical details of the combustion chamber, and finally, we need to rescale the velocity field in order to compensate energy losses in the adaptation stage. As you can see on the right picture, basically, we are initialized a single eddy structure. This is not exactly the same what we have after a complete gas exchange, where we have a multi-edge structure. But this can be considered a good approximation, as we can see together in the next result. About permissive combustion, we employed a model based on the flame area evolution. So basically, we solved a rigorous variable equation to mimic the flame propagation, and in this case, we used a simple deposition model for ignition, and the turbulent flame propagation is modeled according to Peters correlation. About the chemical composition, we apply a strategy where we linear interpolate the fresh mixture and fully burned mixture composition that both are retrieved by tabulated kinetics performed with the OpenSmoke software. This approach is also here used to retrieve for laminar flame speed and Strike's laminar flame speed properties that are corrected to take into account of hydrodynamic instability. So this correlation available in literature allow to take into account about the strong preferential diffusion of hydrogen across the flame front in case of ultra-lean mixtures. And if we move at the result, and here we look at the increasing dilution effect, we have got rather good results in terms of this phenomena. So where the experimental measurements are the dashed black line, while 1D and 3D results are reported respectively in blue and red. However, if we look in deep at the results, we have an increasing underestimation of the ramp, of the initial ramp of the heat release, increasing the dilution, and probably is because of the under prediction of the laminar flame speed, because the correction that we are applying here was developed until a limit of 2.5 lambda, but probably there are also other uncertainties that we need to fully clarify. Then if we look at the load effect, also the load effect is captured, so the experimental trend is captured, but we have a higher underestimation at the high load, and probably this is caused again by the limitation of this correction, which is higher than for the dilution, because the correction of the laminar flame speed here is valid until 20 bars, but as you can see, for the high load condition, we exceed 100 bars. So there is room of improvement, but we can see that first results are really promising also with this simplified methodology. Finally, let's complicate a little bit our CFD methods and try to simulate the whole full cycle again with the portfolio injection, but applied to the fly engine. The fly engine is characterized by a flat head, central spark plug, and a symmetrical piston ball. Here we have a rather high swirl ratio, and the hydrogen injection is completed about 120 degrees before intake valve closure. Here we focused our analysis only on ultra-lean condition. So here we have a full methodology where we need to do a complete 3D full cycle simulation. First, we need to start from the 1D analysis of the engine schematic in order to retrieve boundary condition for 3D. So time varying pressure and temperature at inlet and outlet, and the temperature at walls. Then here we tested two different strategies. So on the left, you have assuming that the PFI injector works properly and everything is homogeneous, we apply an homogeneous hydrogen air mixture at the inlet, and so we can shorten a lot the computational domain. On the right, we have a complete engine, so a complete intake manifold where we need to simulate hydrogen injection. And so in this case, we apply the boundary condition of a wider computational domain, while on the lambda homogeneous, we have a shorter domain that allows to reduce computational effort. In this case, about the mesh, if we look at this last configuration of lambda homogeneous and looking at the exhaust valve opening, we have a full engine domain, again, non-oriented mesh, and with specific refinements to properly capture the details of the combustion chamber and also of particular position of the valve, like at the minimum lift, because we need to properly reproduce the flow inside this narrow region. About the piston and valve motion, here we employ a mesh deformation approach. So namely, we deform the mesh until it is valid. Then when the validity limit is overcome, we need to redo a new mesh and so on. So to cover a whole cycle, we employed several meshes with deformation. From the movie, you can appreciate how we are able to modify the refinement according to the movement of the valves in order to optimize the description of the fluid dynamics and also to minimize the computational effort. In this case, we built up 84 meshes with an average cell size of 500,000 cells. And here, the generation time is rather low because it was run on a laptop for processor 8 hours. The time doubles if we need also to model hydrogen injector, PFI injector, because we need to properly refine the mesh nearby the injector, and we have a wider 3D domain. About the injector, same strategy employed for the surface. So we extrude the mesh here not only to position the inlet far from the nozzle exit, but also to have a cell oriented as the inlet of the hydrogen. And this minimize computational issues. About inlet boundary conditions, similarly to the surface, we imposed a mass flow rate and a total temperature. About the Prometheus combustion model, I don't know into details because it is the same approach that we used for the Penny engine. So looking at the results for the hypothesis of lambda homogeneous, first during the intake stage, what we can see that if we look at the black line, the numerical 1D results, and the blue line, the numerical for the results, we have a good match between them. But the approach is consistent because we applied the 3D schematic boundary condition from 1D. However, we have here a slight overestimation of the pressure at the intake valve closure, which generates a next overestimation of pressure at the spark advance. Therefore, the final combustion that we simulate in our 3D tool, so the blue line, is overestimated with respect to the experimental red line. But this is consistent with the 1D model. So, namely, we think that by improving the calibration of the 1D, we are rather confident that our 3D results will significantly improve, despite the shape is rather similar to the experimental ones. What happens instead if we simulate the post-fuel injection? Do we reach a good homogeneity inside the cylinder? Is there any accumulation of hydrogen in the intake manifold? And to do this, we do need multiple 3D cycles because we need to reach steady-state injection condition. And as you look by the movie, after the cycle 0, we look at an accumulation of hydrogen. So it is fundamental to do more consecutive cycles. And here we simulated 3 cycles. And if we look at the hydrogen mass distribution over different lambdas, a two instant of interest, like intake valve closure on the left and spark advance on the right, we can first observe that from cycle 0, the blue, to cycle 1, the red, we have a variation. So it means steady state conditions are still not reached. While at cycle 2, basically, we are almost already yet at steady state features. Then, if we compare these results with the target air-fuel ratio that we would like to reach, we see that the compression, so moving from IVC to spark advance, helps a lot in the homogeneity. And also the spark advance, we do not have a perfect homogeneity because in this case, we have some internal recirculation of exhaust gases. But also curiosity is if we look at the volume share occupied by this small stratification, we can notice that despite the majority of the mass is very close to our target, the volume occupied in the cylinder is more occupied by the richest mixture because of the properties of hydrogen. So hydrogen is characterized by a high specific volume. And so if in case of a slightly richer mixture with respect to our target, its occupancy of volume is wider. And so we have this slight mismatch between the mass stratification and the volume occupancy. So in conclusion, we can see that with our methodologies, we are able to study 3 different hydrogen internal combustion engines by modeling 2 different injection strategies, so direct injection, port-fuel injection, and we also have simplified techniques, so we are able to initialize condition at IVC and do fast simulation also in 3D. But we can also do complete gas exchange simulation to increasing the quality of the result. And finally, we're also able to simulate premixed homogeneous alkyl hydrogen combustion. About stratified combustion, Tommaso will show you something tomorrow. But anyway, what we can conclude is that with LIBAIS, we have a rather wide set of validated methods to model spark ignition hydrogen engines. However, this is only a starting point. So there is a lot of room of improvement. In fact, the code is always under development in order to improve the experimental numerical consistency, to minimize the computational cost, and also to ease the user-friendly approach. And so my suggestion is stay tuned, because new developments will come soon. So thank you for your attention.
Thank you, Lorenzo, for your very interesting presentation. I see several questions from the audience, so I start from Benjamin.
Yes, it is.
One estimation.
No, first, about your first question, we noticed an underexpanded jet, but it is not so underexpanded like a direct hydrogen injection. So you do not have that normal shocks. You have some expansion fans, basically, but it is a mild underexpansion because of the injection pressure are much lower. Then about mixing, these are very new results. So these are, I also have a look at the results, I think 2 or 3 days ago, and we noticed that the mixing improves also during the intake, but also in compression, because we have some internal gas circulations. And so, because here we have a swirl motion, also the motion is important for the mixing in this case. Also, if hydrogen has a lot of diffusivity, basically the average motion of the fluid impacts a lot, and the gas circulated stays basically in the central part of the engine in this case because of the swirl, and they are accumulated nearby the spark plug, and so you have a slight stratification. So it is also important, the engine design, to have a full homogeneous mixture also with hydrogen inside the engine.
Hi, Lorenzo, thank you very much for the very. I have a question, actually, maybe I missed that. You need a special treatment for the early current spark?
About here, we simply applied the deposition model. So basically, we initialize burn mixture in some cells around the spark plug, and then we have a special treatment to do the transition from laminar to turbulent condition, and we do it by means of Hervé-Gemaly approach. So basically, we have a 0D model, a 0D kernel model that apply its predictions on the Eulerian side. So it is a lighter version of our Lagrangian detailed model. But yes, we have a special treatment.
Yeah, thanks.
Thanks for the question.
I have two questions, actually. On the
Right.
Looking.
Yes, we have a look at that. We also look at the literature that there are some results that some groups that propose to modify it to increase the diffusivity, but probably we think that it is a matter of also not only hydrogen diffusivity, but main flow structure, because here I cannot go back quickly, but we still have some a not perfect matching of the tumble motion generated by the hydrogen injection. And probably by improving it, we can better improve probably the diffusion, because in our cases, so the bottom results, the vortex is more concentrated and probably keeps the hydrogen there. Also, if hydrogen diffuses, but the motion, as I probably said to Benjamin, impacts. If you have a global average motion, tends to confine the hydrogen. So probably it's not a matter of Schmidt number, but it is a matter of flow structures that should be improved in this for the engine.
Second question I have. What did you do with low temperatures?
About temperature, so we impose as a fixed value temperature at walls from 1D, so there is this limitation, but flame interacts at walls, considering that we model the thermal diffusivity according to the turbulence of the cell at the walls, and so we model the thermal losses with this, but we impose temperature at walls for now. About you asked about okay, knocking, yes, in this model, we do not have a knock model, but we can do it. So if in case of need, we also have this possibility, yes.
Very see a lot of sensitivity.
No, we did a sensitivity analysis about wall temperature, but not on Sophie engine, on Penny engines or Valencia engine. And with hydrogen, increasing the mesh refinement at walls and properly capturing that part of the story, you improve the results because of the lower quenching distance of hydrogen flame to walls.
Variation.
So in these cases with the closed cycle, we simply developed a methodology to do a fast assessment. So basically, in the Penny engine, so the Pentorf Valencia, basically we didn't do full cycle, closed cycle inside integral closure to provide the first results for the industry, for example. We need to understand if the engine is okay. Then to go in more details, we do full cycle. And in this case, with the methodology applied to the last engine, the Fly engine, we simulated combustion with multiple meshes. So the approach is fully consistent. We didn't remove ducts. So everything is inside. We do the gas exchange. We keep the ducts separated. We continue the simulation. We do combustion inside the cylinder and go on. Here I presented only multiple hydrogen injection without simulating totally the combustion, but simply imposing burn condition at the exhaust valve opening. But because this is a first step towards the multi-cycle combustion with the gas exchange, so simply a matter of refinement of results that you need. So, no, the advantage is the CFD, so the computational costs first, and you can try to do a lot of tests, also varying the shape of the piston, for example, because maybe you need to calibrate, you know anything about the engine, you need to design from scratch or do some improvements or change the fuel. And so you need to simply understand if a new fuel or a new strategy of pressure is good with that kind of engine quickly with some fast 1D results. Otherwise, so it is only a matter of approaches that if you need to do it fast, you can do to achieve some first preliminary results. That could be a starting point for the gas exchange.
How much time?
How much time? Okay, about this is interesting. So we would like to select the configuration and consistently compare the two approaches and provide time saving. So the idea is to do it before the end of the year to do a comparison, because now we are studying the Penny engine with complete gas exchange, and so we will have this amount in terms of computational saving. So this is a good question, and we are curious to understand this by doing combustion, because here, okay, only no reacting. But we need to do combustion and see the impact, because what we saw is that impacts the distribution of hydrogen immediately after the end of injection. But then you have still time to mix it up. It is pure. I'm curious to see what happens, but you need to simulate a stratified hydrogen combustion. And when we did these results, we were not able to do this. Now we have an approach to consider a full stratification of laminar flame speed for hydrogen, also for ultra-rich and ultra-lean mixture. And so we will do soon, and we are curious. I think with combustion, we will have an answer.
Yes, maybe I missed it. So, concerning this case of the DI, you will make the simulation with a closed loop.
Yes.
Yeah. So you do need an initial condition to start.
Yes.
From the experiment.
Yes, because basically there are two cases: one without tumble and one with tumble. Now we also simulated the tumble one, but we started from basically flow at rest. So these are PIV measurements. And then basically when you have the injection, the flow, so in the case without tumble, is totally driven by the injection of the hydrogen, because you have a high velocity, high momentum, despite the hydrogen is.
I was wondering why you have that.
Okay.
Yeah.
In
so
fact, this is.
One motivation could be that you have some discrepancy in the initial. The other one could be also that you are considering only a sector.
No. Here we are considering a half engine domain. So basically, it's like considering. Okay, we can try to consider all, but it is symmetrical, so it is not a sector. This is half engine domain. So here it is a good point. So I mean, we think that we need to improve this like tumble, but this tumble is basically generated by the hydrogen injection, basically, because it is totally driven by the injection. So probably it is a jet wall interaction that we'd like to probably to improve.
Yes, but I agree with you that maybe it's a problem with convection.
Yes, it is probably something about convection.
Okay. Any other questions?
Okay. Thanks for the presentation. Just information on both stroke and FBM.
What engine type? Okay. No, okay. I provide all light duty. So basically, 0.85, 0.84. The stroke are more or less the same. So are all comparable. The rotational speed is usually 1,500 RPM, but are all light duty engines. So all similar, but change the shape of the head, the piston, and so all configuration.
Okay, thank you, Lorenzo, again for your presentation. And now move to the next presentation. Next presenter, she's Victoria Kubler-Tesch. Am I right?
Yeah.
Okay. Technical University of Darmstadt, and the title of her presentation.
This.
Yeah.
Thank you, Lorenzo.
Just a second. Oh, because we would like to remove the power. Okay.
Okay. Title of our presentation is on the development of preferential evaporation in isooctane ethanol spray.
So thank you for the introduction. Very nicely introduced. Today I will be mainly focusing on lots of the model development and then the approach there, so which steps we're taking, and then I'm going to show you some intermediate results. But first, let's go to the motivation. As you can see, most of the greenhouse gases in the transport sector are created by internal combustion engines. And with the climate crisis, we know we need to improve those and improve the combustion engines because they are still mainly in use. And wrong direction. And however, those modern combustion engines have more stricter requirements. For example, we expect them to have low pollutant emission and greenhouse gas, but also soot emissions. And we also want them to be CO2 neutral fuels. And here, ethanol as a promising renewable fuel is introduced. This is what I'm focusing on. And actually, there was a New York Times article 3 weeks ago where they showed that in the US politics, a ban on E15 fuels was lifted. So we will see more ethanol maybe in the US. With those news, and we also expect those new those ICE engines to still have a higher combustion efficiency. With the new fuels, we have new challenges. We will have different spray and mixture formation, which will inherently affect the combustion. And in my presentation, I will be focusing on the spray formation and here on the model development. So we are using in OpenFOAM the Euler-Lagrange method. Here we're describing the liquid in parcels, which we are following. And here each parcel represents a collection of identical droplets. If we're looking into the particle modeling, we have a particle, we have some flow around it, and we solve the momentum equation, and we assume the particle to have a drag force and gravity to act on it. And we're also solving some sort of an energy equation. So here we're looking at the temperature of the droplet, which is affected by convective heat transfer, here shown with QS, and also which is affected with by the evaporation happening in the droplet. Yes, which is modeled this way. So that way we have a temperature equation, and then we're also looking with multi-component fuels at the species in the droplet. When we look at the species, we're looking at the interface here between the liquid and the gas phase, and here we assume a vapor-liquid equilibrium, which with multiple components will lead to preferential evaporation, and usually it is modeled with ideal liquid and gas. However, also the species usually affects the heat transfer, so those are strongly coupled. However, when we model the evaporation, here is shown the term for the mass transfer from the droplet into the gas. We're using the Stirling mass number, which looks at the gas mass fraction at the surface and also at the gas mass fraction in the far field. We're using that for the species transport. And at the surface, we're in the ideal case, we're assuming Rolle's law, which looks at the mole fraction at the surface, which is dependent on the mole fraction in the liquid, its vapor pressure, and the pressure in the gas. And somehow this thing got turned upside down, which I don't understand. But what the takeaway of this figure is supposed to be is that when we model an isooctane ethanol droplet, that in the ideal case, ethanol is always the more volatile fuel. So never mind the isooctane mole fraction, there will always be a higher ethanol to isooctane ratio in the gas phase than in the liquid phase. However, this is not the case because if we're looking at the real BLE, you should be seeing here. This is shift, so maybe shift the perspective. With high isooctane mole fractions, we still have the case that ethanol is the more volatile fuel. However, with high ethanol mass fractions, this is not the case. There, isooctane is the more volatile fuel. And we do also have an isotropic point. So we want to model this, a real VLE. We need to look at the basics. We usually assume an isofugacity condition, where it means that we have the same fugacity in the liquid as in the gas phase and the vapor phase. And then you can model the fugacity either by using a phi or a gamma approach. Here, in this case, the vapor phase is modeled with a phi approach, and the liquid phase is used with a gamma approach. And I've also shown that here the phi is the fugacity coefficient, and the gamma is the activity coefficient. And then the way you could get the activity coefficient, for example, is by using an activity coefficient model, which in our case we often use UNIFAC, which then calculates the activity coefficient dependent on the temperature, but also on the composition. If we then simplify this by assuming an ideal gas phase, we have an equation that is dependent on the activity coefficient and the composition of the gas and liquid phase. And this needs to be, would then need to be calculated on runtime. However, the disadvantage of activity coefficient models is that they're limited to certain pressures. So a different approach could be to use a tabulation. The advantage of this is that this is actually feasible for multiple pressures, could also be used for diesel engines. And here the approach would be to start by obtaining VLE data, either by tabulating this or using experimental data. Then you could generate a table for a bicomponent fuel. This is straightforward. And then you could use a lookup during the runtime in OpenFOAM. So you would get the mole fraction depending on the set pressure and also the particle temperature. So the approach of implementing this is we start with a single droplet model, and so going from the very basics, then moving on to a droplet chain where we actually have different mixture formation already happening. So the droplets have an impact on each other, and then moving to the most relevant case of the spray. So the idea is that we have validated actually all of this, the droplet chain, and then we can create some results with the spray. And this is all accompanied by experiments from LTT Erlangen. Yes. Just a quick introduction on the single droplet. We had a single droplet which had 70% of ethanol. So this is the part that we have different results depending on, we have very different results depending on which approach we're using. And here in the figure, we see the mole fraction inside the liquid droplet. So we have a high ethanol in the beginning, very low isooctane, and when actually this droplet starts to evaporate, yeah, it does, is that we have different things happening. Here with the real VLE, ethanol starts to accumulate in the droplet, and isooctane is the species that evaporates off. And in the ideal droplet, we have the opposite effect. So isooctane is accumulating there. So we're seeing in the droplet, different species are accumulating, which also will lead to a different mixture formation in the gas phase. The next step is the droplet chain. Here I will introduce to you the experiment really quickly. We have a droplet generator, which has fuel coming inside, and then we can create different initial droplet sizes. They're between 30 micrometers and 100 micrometers. We have a very small field of view of only 4 millimeters. And then in the next experiment, the droplet diameter is measured and also the isooctane ethanol ratio inside the droplet. We will vary the initial droplet diameter, initial droplet temperature, and the fuel composition to get a comprehensive overview. And we actually did this at ambient temperature. You can see here the droplet chain forming. And at ambient temperature, actually not a lot of evaporation is happening. We also saw this. in the simulation, so you can see barely a change of the droplet diameter. So the goal is to also vary the ambient temperature. After that, I also looked at, this is an ideal droplet chain. We looked at, I looked at different ethanol concentrations at a high temperature. And what you can see here is then low ethanol volume concentration, isooctane also starts accumulating in the droplet. And unsurprisingly, the same happens for the ethanol. Droplet, which we expect to see a different result here with a real VLE. Lastly, we also looked into a spray G condition with two different fuels. One of them is a 3-component fuel of N-pentan, isooctane, and undican. And then also at a 9-component fuel here called PACE 20, which contains roughly 10% or volume percent of ethanol. And we modeled those after some experimental data. And what was here the focus on was actually the mixture formation in the gas phase. So the way this was modeled is they looked at the ratio of the low volatile fuel for the 3-component fuel. This was an undican, and relative to the other fuel and all other fuel components. And what you can see here is that there's of course some segregation. So most of the low volatile fuel is close to the nozzle. And if you look at this with the PACE 20 fuel, you can see that there's a lot same modeling of the low volatile fuel was used with those 3 fuels, that there's a higher segregation in the spatial area of the mixture. This is also done with an ideal VLE approach, and we actually matched this case pretty well. You can see the segregation very close to the nozzle, and yeah, we this actually done quite well. But if we look at the ethanol, the fuel containing ethanol, we do see high discrepancies, and yes, the segregation here is of course also higher. And yeah, this will be interesting to analyze with a real VLE. Yeah, I think that's it. Just as a summary, I introduced the modeling approach of a real VLE, and this will be implemented in OpenFOAM. And the approach here is to increase the complexity and validate during the whole implementation steps. And in general, the outlook is that I hope to present the results of the real VLE sprays. And I think the step after that would be to also look into combustion characteristics with those with the different mixture formation. And this will actually be very interesting because we know that alcohol fuels, actually, this is the case of a diesel engine, have a very different combustion characteristic. So here in this diesel spray, we see that alcohol fuels actually have a higher ignition delay time. So it will be interesting to see how this actually affects gasoline spray. And here I'm at the end. Thank you for your attention. And I would also like to say thank you to all my colleagues and my boss. Thank you.
Thanks, Victoria, for your presentation. Questions?
Hi. What do you mean?
For modeling the gas phase.
Yeah, so the vapor liquid equilibrium. So how those interact.
How do you transfer it to
The question is how I model the rest of the gas phase, or how I.
How do you? Because you have these
Yeah.
gas around the drop.
Yeah.
How do you couple it?
So in Euler-Lagrange, we have a source term in each cell for the what part of the liquid is transferred to the cell, and what I'm wait, go back to some slides. Okay, so this is the case of the really. So this is the term I'm solving in OpenFOAM, and I mean the y infinity I is from the cell, and this is the part that I'm calculating. And so the mass transfer depends on this mass fraction here, which I'm calculating depending on the VLE on the surface, and this is something that is dependent on the initial initial composition of the droplet, temperature, and the pressure. Yeah.
More questions? Yes, please.
Yeah. Yeah.
Yes. Imagine that the next step will be the pressure inside the droplet. I understood.
So the next step. So this is when we inside the droplet.
Yeah.
Actually, I'm first doing the real VD on the outside, and I don't think 1V in a spray will be feasible to calculate during runtime. So I'm currently focusing on the VD on the surface and implementing the real thermodynamic model.
So the next step will be in the spray to still consider the 0D.
Yeah, I'm still assuming 0D in the droplet.
Any more questions? I have one.
Yeah.
You show that you are tabulating the saturation molar fraction. So that
You mean this one?
yes, you pick
Yeah.
up excess and you put it in the Spalding formulation, but this is taken from a table instead of calculated, I guess, from a correlation. How long it takes to generate a table?
I'm unsure. I don't think. I mean, I think the hard part is, table generation for bicomponent fuel is rather simple.
Oh, okay.
Yeah.
Okay.
I mean, bicomponent fuel. The more components you have, the more complicated it gets.
Thank you very much. If there are no questions, let's thank Victor again. Introduce now. Next speaker is Giovanni Caramia from Politecnico di Bari. Yes, sir.
No, vorrei la presentazione modalità relativa.
C'è un problema, Timo. Se tu la metti.
No, e allora lascia stare. Non ti preoccupare.
L'unica cosa che quando ti registrano, su YouTube vedrai la modalità relativa.
Come per me va bene.
Okay, title of Giovanni's presentation is modeling hydrogen injection for internal combustion engines using Wino schemes in the OpenFOAM framework. Please, Giovanni.
Yes, I'm going to present my work developed together with Professor De Palma. This is the outlook. I will introduce the argument, and I will afterward show the numerical method, the simulation setup, and I will show you the degree refinement study, the results to end with conclusions and future work. Hydrogen can be used in internal combustion engines to zero the carbon-based tailpipe exhaust emissions, and in-cylinder direct injection is preferable to avoid preignition and backfire, as well as to obtain high volumetric efficiency. Hydrogen's low density requires high injection pressure for fast hydrogen penetration and sufficient in-cylinder mixing. these high pressure injection pressures determine chocolate flow condition during the injection, with the result in the formation of turbulent underexpanded jets. Understanding the underexpansion process in turbulent mixing just after the nozzle exit is necessary for the designing an efficient hydrogen injection system and strategies. Here, I'm showing the complex structure of the jet just outside the nozzle exit. And here we can define the NPR, the nozzle pressure ratios. We will investigate many different values of this parameter. And here I also highlighted the two main characteristic parameter of an underexpanded jet. It has the Mach disk high, I hope this one, and the Mach disk width. You can note that the structure is very complex, so the need of a high accurate scheme for low dissipation and good shock capturing is needed. Okay. The governing equation. Governing equation are the typical Favre-Reynolds average Navier-Stokes equation, solved with the K omega SSST turbulence model. And here the numerical method. Unsteady runs using obviously OpenFOAM. The axis symmetric discretization, so to have a lighter computational effort. We use the second order accurate Frank-Nicolson time integration and the Wino schemes for advection terms. Different order of accuracy, we consider the different order accuracy for weighted, essentially non-oscillating schemes. For the diffusion terms, we consider the second order accurate linear scheme. And for pressure velocity coupling, we use the Pimple strategy. For instance, the OpenFOAM solver name is raw reacting Pimple foam. Regarding numerical method, we have to cite the work of Gartner, which developed the Wino scheme inside the OpenFOAM library. Here we start with the simulation setup. Here are depicted the nozzle geometry, and I also wanted to show you the grid structure, grid, near the nozzle exit and inside the nozzle. As you can see, here there is the domain, the computational domain. We call it the short one because we used it to better investigate the jet structure near the nozzle exit. While we used a longer one with a local grid refinement to better understand the hydrogen diffusion process inside the chamber. The simulation setup, initial and boundary condition. The simulation initial and boundary condition consisted in the rest condition as initial condition, and it was assumed that hydrogen occupied the entire high pressure reservoir and a tiny part of converging nozzle up to the 1.5 times the diameter value upstream the nozzle exit. Air occupied the low pressure ambient and the remaining of the in-nozzle volume. A curiosity, it was possible to use a slip condition inside the nozzle because of the verified Knudsen number. Now we are at the grid refinement study. We consider a value of MPR equal to 10. We here consider the MACDISC high as a parameter. Considering an experimental value of 3.05, and our grid refinement study dealt also with the use of different discretization schemes. Here, the XX identifies the number of cells at the nozzle exit in the flow transverse direction, while we know X identifies the order of accuracy. So we know 1 is second order, we know 2 third, and 3 a fourth order. As we can see, we reached a good agreement with the experimental value and the stabilization of the calculated value, considering we know 3 and the 40 as grid refinement level. The same is for the MACDISC width. And now what we have obtained with our computations. Here it is easily noticeable that the structure of the flow resembling the sketch I presented before. The MPR values. Varying the MPR values, the structure of the flow changes. Counterintuitively, the number of barrel shock cells, where a barrel shock cell is this structure here, the number of these cells decreases when the MPR values increase. Something similar, this is the Mach number on the bottom part of the computational domain, and we can see two things mainly. The first one is that as the MACDISC I increases as an MPR increases, and the presence of secondary MACDISCs that vanish in the same way. The message of this slide is why to use higher order discretization schemes, because with these schemes we can capture instabilities that the lower discretization order schemes do not capture. Specifically, on the lower part on the left, we can see the Kelvin-Helmholtz-like instabilities using WINO 3.0 discretization scheme, where with WINO 3.0 I intend the fact that I'm using a fourth order discretization scheme without a limiter. Again, results. This is a correlation between the MACDISC I, essentially, and the square root of MPR's values. We can see that we are with our computation resembling the straight line correlation type. And the other important thing is that the gradient of this line is in good agreement with numerical and experimental, numerical, basically, data available in literature. Not only the Mach, but also minimum temperature and maximum velocity we investigated and confronted with the numerical results present in literature. And even here we reached a good agreement. The last slide regarding results deals with the hydrogen mass concentration as a function of distance from the nozzle exit at MPR 10. Even here we had a good agreement with the experimental and numerical data present in literature. So here we are at the conclusions. The near nozzle under expanded jet structure and the hydrogen jet diffusion have been analyzed by an URANS and WIN model. The method has been validated by a grid refinement study versus experimental and numerical data. Linear correlation for Mach disk high at different MPR's values has been verified. And the advantage of employing higher spatial order of accuracy is clearly demonstrated by the capturing of coherent structures. We have to say that the model tends to slightly overestimate diffusion, in most part far away from the nozzle exit. Future work, improve diffusion model, eventually using machine learning techniques, extract proper orthogonal decomposition or dynamic mode decomposition modes to construct a reduced order model, optimization of the nozzle geometry using a joint approach with automatic differentiation, extension to less and to 3D URANS. About this, I'm glad to present some preliminary results. Here we can see the structured grid used for the computational domain. We can see here the classical butterfly grid with structure. And below, there is the hydrogen diffusion in terms of mass fraction. Firstly, on a plane passing through the nozzle axis, and secondly, as a picture of a 3D evolution. I just finished. These are the references, and I would like to thank you for your attention, and I'm waiting for your questions. Thank you again.
Okay, Giovanni, thank you very much for your presentation. There are questions, please. Maybe when you make your question, state your name and affiliation so that at least we know each other. Thanks.
First one is regarding the I suppose.
Yes.
But it's with connected, and so basically the
value reconstruction on the base, if I remember correctly. Then up modified, yeah, it's modified up, adapted. But it's basically an upgrade. My question is, from the literature that standard schemes like are for sure the best one in terms of. So my question is, it's very interesting to see that actually we are enhancing the knowledge of what's happening that downstream using IoT scheme. I don't be clearly. But my question is, are you planning to simulate this problem also using the central schemes? Of what I just said.
I already done it, and what is the game changer is the calculation time.
And this was my second question.
The calculation time with this approach is really smaller. With the central, I used a raw central form on some other kinds of solver, and they are all very lower in giving a solution. This is my experience.
And in terms of RAM consumption, because you have to create the stencil, you have to.
RAM consumption, it depends on the grid. If you stay with a two-dimensional axisymmetric grid, you have a reduced number of cells. So the time to create the matrices containing the coefficient is really reduced. Regarding the 3D mesh, we are working with the 5 million, not so much, 5 million cells. And on 48 cores computer, it took 8 hours.
Just to create the match.
Just to create the coefficients.
I know I used this, but not for 100.
But the good thing is the fact that you can stay on a axisymmetrical, essentially two-dimensional grid, and obtain results quite comparable with LES results. And you know that LES you have to use a three-dimensional grid for having presenting results.
And in the last slide, you were showing that you are kind of simulating
I've always simulated multi-species flow because I have hydrogen and
all the simulations are
all. I have hydrogen in the high pressure chamber, and I have air in the test oxygen and nitrogen.
My question is about numerical stability of the properties of the value speed, and I expect that it's quite free to get
yes, the instability is present, is really a crazy horse, and but you can treat it reducing the delta T. I have the delta T similar to those of NLES computation.
Thanks.
Thanks to you.
More questions? Michele.
Thanks for your nice presentation, Michele. I wanted to ask you a comment about the non-state condition.
Yes.
Is it for PV or for any prediction change?
No, I've taken. Yes, I've taken it reading the work of Gall et al., I think. I noticed it. And even reading the work from Angelo, I hope the pronunciation is correct. That condition is imposed to avoid a great number cells usage inside the nozzle to resolve the boundary layer. In this way, I have a reduced number of cells inside the nozzle, and even with this reduced number of cells, I do not have misleading velocity vectors or flow structures that are not true. That's it. I do not I did not carry on this particular analysis, but reading the work of in the references, they were telling just this. You can go with a reduced number of cells using sleep condition. That was even for me something strange, but as you can see, we use it as a reference also experimental values, and we reached a good agreement.
Okay. Thank you. Okay. Any more questions? Okay, so let's thank Giovanni again.
Thank you.
Okay, so now we have next presentation is about 0D, 1D model of internal combustion engine. Angelo Onorati from Politecnico di Milano. His presentation title is the Gasdin code for 0D, 1D simulation of internal combustion engine fed with renewable fuels.
Provo a interrompere la condivisione giusto per essere sicuro che... Okay. Perché avevi così corretto.
Already. Thank you very much, Tommaso, for your kind introduction, and good morning, ladies and gentlemen. Very glad to be here to give this presentation about Gasdin, the code that we developed since a long time. I started my academic career with Gasdin, and I'm still continuing, so it's my pleasure. First of all, some acknowledgements. I prefer to thank our group, Internal Combustion Engine Group, without listing all the names, and Sursum. Sursum is the spin-off company that we recently founded a couple of years ago, and they are involved in Gasdin applications. Okay, so the outline of my presentation, I will give you a brief history of Gasdin. I will show you several configurations of different engines that we simulated, and I will explain some 0D, 1D simulation models that we develop and apply. In particular, I will highlight the importance of new fuels, renewable fuels, hydrogen, ammonia, and others, and I will show some recent results. Why are we going to talk about 0D, 1D simulation in this session? Because as you see from the previous presentations, it is always important not only to give the boundary conditions calculated by 1D models to 3D simulations. So temperature, pressure, pressure pulses, these are important boundary conditions, but also to compare the simulations of 3D models and 1D models to check the consistency and verify the quality of calculations. Just an example, this is a complex schematic, one of the most complex schematic, 1D schematic that you can develop by the Gasdin interface. It is a 4-cylinder engine with turbocharging, in particular with dual stage turbocharging, 2 turbines, 2 compressors, an intercooler. You see 2 turbines, 2 compressors, DGR, low pressure EGR circuit, high pressure EGR circuit, the EGR cooler, the silencer, the after treatment system. So you see a very complex engine in which we can calculate, of course, the unsteady flows, the pressure pulses propagated in the intake and exhaust system, the combustion, and evaluate performances, fuel consumption, emissions, and so on. We started developing Gasdin more than 25 years ago, and the name Gasdin was given in 1998. I gave the name, just to tell that. And so at the moment, our group is busy with 2 important fields: the development of LibEyes, the set of libraries in open form that we are discussing right now, but also we are working on Gasdin, new developments, new routines, new solvers, new boundary conditions, in collaboration with Sursum, which is the spin-off, which is in charge for managing the Gasdin activities. So I will show you some different examples. These are recent engines that we simulated during the last couple of years. For example, on the left, you see a 3-cylinder spark ignition turbocharged gasoline direct injection engine for the Renault Captur engine that we investigated in detail during our European project. You see the complete schematic of this system from the intake to the exhaust. And on the right, a high-performance motorcycle engine, a 1-liter 4-cylinder MV Agusta engine, in which, if you have a look, you can recognize all the typical elements: pipes, plenums, injectors, junctions. This is, for example, a 4-into-1 multi-pipe junction, the after-treatment system, the silencer. So these are recent schematics that can be well managed by the interface. Just to remind what are the fundamental equations for a code that is in charge of solving the steady flows. So the 1D conservation equations for mass, momentum, and energy, considering so the compressible and steady flows with transport of chemical species that are listed here. We have a model that can also track the chemical species. We can vary this number of species, and in particular the chemical species needed depending on the specific problem. If we inject ammonia, if we inject methanol, if we inject hydrogen. And of course, then when we calculate the emissions, we need to track different chemical species. During the years, we have developed different solvers for Gasdin, both finite volume solvers staggered in space and time, and finite difference solvers that in general guarantee a good accuracy and robustness, and also the computational time is acceptable. Now, what about the combustion model? There are several announcements in the combustion model, which is based on a quasi-D approach with multi-zones. In the combustion models, we can take into account the premix combustion, the non-premix combustion. In this case, for example, we have a premixed combustion, and in a recent development, we can introduce empirical correlations for the calculation of laminar flame speeds, but also a tabulated kinetic approach that is, of course, more accurate, taking into account the nature of the fuel, hydrogen, of ammonia, or other fuels. So these tabulated laminar velocities are important for a better prediction of the flame front propagation. In this model, we also have kinetic submodels for emissions, NOx and others. Okay. Now some examples, just to mention some activities that are going on in this period. This is a single cylinder ammonia fueled engine that we are calculating with GASDIN, and we inject ammonia in the pipes, transport the ammonia, and then we carry out combustion of ammonia in the single cylinder engine in collaboration with Orleans University. We have some experimental data. There are different models that we are applying and further enhancing, developing. You can see here a comparison between experiments and simulation in terms of rate of heat release, which has been imposed so that we have a good match. And then, of course, we are going on with these investigations concerning different operating points with different equivalence ratio and so on. This is important to give boundary conditions to the parallel CFD simulation of the same engine that we are carrying out at the moment. Just to mention some work going on to enhance the combustion model, we are now working to introduce this RCCI simulation capability so that we have a low reactivity fuel coupled with a high reactivity fuel directly injected in the combustion chamber. We are working to enhance the model to introduce the effects of these different reactivities in the combustion model to take into account, for example, that we can inject ammonia in the pipe and then add, for example, a pilot injection of diesel fuel or HVO, whatever you like. And we are enhancing the model to cope with this challenging topic. This is another engine we are simulating, another single-cylinder engine that already Lorenzo mentioned before me. This is a collaboration with CMT Valencia. This is a single-cylinder hydrogen engine with port fuel injection that we are simulating in detail. You can see here some comparisons in terms of pressure waves. Pressure waves, green is calculated, black is experimental, with some details that are important, because if you well capture the wave motion, also the mass flow rate into the cylinder is well captured. And here you can see 3 operating points with different lambda 2.4 and very lean 3.4 and 1.6 on the left, and the corresponding PV diagram calculated by GASDIN, which is, of course, a good step. We are considering many, many other operating points at the moment to evaluate also emissions, to evaluate other typical quantities of this hydrogen engine. And now a concept that we are investigating with GASDIN, which is a virtual engine. It is not existing at the moment. This is a V8 hydrogen engine. You see the V8 configuration highlighted here with the 4-into-1 exhaust junction, turbocharged with PID controllers in order to investigate the potential of this high-performance engine. In this case, we are now calculating not only the performances that can be achieved by different lambda. Of course, we can predict a possible map of lambda values to keep under control the NOx emissions, which is the only critical issue of a hydrogen engine, NOx. So we can work with different lambda from very lean to moderately lean. We can calculate different operating points at full load, part load. Here is a cloud of operating points that we can calculate when we consider the coupling of this engine to a virtual vehicle, and we consider real drive emission cycles. So on these operating points, we can evaluate fuel consumption, emissions, NOx, and optimize the schematic. Then, of course, we need to model also the after-treatment system in this case. That's why these are preliminary calculations that have been carried out recently in terms of cumulated NO, cumulated ammonia, and temperatures. You see inlet red and outlet blue. So introducing an SCR, selective catalytic reduction catalyst, in the after-treatment system, we can calculate what is the abatement of NOx during a real drive emission cycle, an operating cycle. And it is evident that selective catalytic reduction system with injection of hydrogen, with use of hydrogen, is very useful. Here you can see the list of chemical reactions that have been included. We can evaluate also the temperatures, inlet and outlet. So this is, how to say, an ongoing research work to enhance also the after-treatment models for SCR and for catalysts, for everything. So we can couple the engine, the fluid dynamics, the steady fluid dynamics of the engine and in the exhaust system with the after-treatment system as well. Continue with another example of an industrial engine, a 6-cylinder turbocharged engine that initially in the original version is fed with natural gas that has been converted to hydrogen just to see the reaction, just to see the potential of this industrial 6-cylinder engine, introducing a port fuel injection of hydrogen, changing the turbocharging, of course, because we need to recover the torque and the power. And it was possible to guarantee a good volumetric efficiency with low NOx emission thanks to very lean lambda equal to 2 in this case. So this is another example of a complex heavy-duty engine. Now, some examples just to complete the picture. This is a single-cylinder engine for high-performance motorcycle application, a single cylinder that was investigated for the Moto3 championship. And you can see some comparisons between calculated and experimental quantities for, you see, torque, power, pressure waves. The red is predicted. So we are confident that Yazdin can give a good representation of the engine. So this is the virtual engine that is working more or less like reality. I can continue with another motorcycle engine. This is a V4 high-performance motorcycle engine that we investigated a few years ago, just to highlight the complexity of the intake and exhaust pipes, the silencer, the junctions, and the comparison. You see the validation that is carried out considering measured pressure waves and calculated. These details are important when you want really to stress the capability of the model. And this type of accuracy is very important to achieve a good simulation of the whole engine. This is another example that we recently investigated. I mentioned already the 3-cylinder engine by Renault. It is a 1-liter gasoline direct injection engine with intake and exhaust pipes, turbocharged. We introduced PID controllers for the boost, for the air-to-fuel ratio, and so on. And here you can see a comparison between measured and predicted maps of brake-specific fuel consumption in gram per kilowatt hour. Just to give you an idea of the capabilities of a 0D1D simulation model, this is the map of all the operating points that have been simulated, full load, part load, different engines, by means of an automatic calculation of all the operating points. Then you can plot the map with any quantity of the fuel consumption, CO2, NOx, and compare the map. And overall, it is essentially quite satisfactory. I can show you some details of pressure waves for the same engine. So measurements that were carried out in Valencia, again, thanks to the good collaboration with CMT. You see pressure waves calculated and measured, PV diagrams for different operating points for this engine. Continue with, just to mention, what we can do also with this model acoustics, silencers. Mufflers are complex pipe systems that can be coupled to the engine, of course, for pressure losses, but also for gas dynamic noise and for the calculation of transmission losses. In the frequency domain, you see the comparison between measured transmission loss and predicted for different complex configurations. So with perforates, with sound absorbing material, with the flow reversal, with all the typical components of silencers. This is another important aspect. So the acoustic features of an exhaust system. To complete my discussion, I would like to mention the possibility to couple gases with open form, because of course there are two different worlds, 3D simulation, 1D simulation, that can help each other, but we decided to strictly couple open form and gasing. So it is possible to have a complete gasing 1D model of an engine, but then you can substitute a simple 1D domain with a 3D mesh where needed. For example, in the intake system, in the exhaust system, you can put junctions, you can put plenums or other components in 3D. And the two domains are strongly coupled numerically by means of Riemann solvers so that you can play with open form and gasing and capture more details. I will show you what I mean. For example, this is a V4 motorcycle engine for which we have a complete 1D schematic with 4 cylinders, with intake system, exhaust system, silencers, but the intake system is quite complex and a simple 1D approach is not always satisfactory. If you want to capture some more details of wave motion in the plenum, you can introduce a coarse mesh representing the intake system. Here you recognize the trumpets, 4 trumpets, 1, 2, 3, and 4. The airbox that has been modeled in 3D with a coarse mesh, which is enough in this case, and coupled to the unsteady flows calculated in gasing. So we have a 1D domain with pressure pulses and a 3D domain coupled numerically so that we can capture the complexity of the wave motion in the intake system. You see on the left the evolution of waves that are not one-dimensional. Waves are one-dimensional in the pipes here, planar waves, but in the 3D domain, you see that waves propagate longitudinally, transversely, and this can have an effect on the volumetric efficiency. That's why sometimes we wish to couple 1D and 3D codes like gasing and open form to improve the prediction. Thank you. That's all.
Thank you. Thank you, Angelo, very much for your presentation. Before the question, just one information. If possible, we just stay 5 minutes to make the conference picture. So stay here, don't go away after questions. Questions for Angelo.
Just an answer to your question, Angelo. Thank you very much. I think it's very important to see that we have a full grip on what's happening in 1D, and I think this is very important, especially when it comes to coupling of our advanced concept. I was wondering, when you think about the silencers, I think this, acoustics is always a difficult thing to capture. And so I was wondering, how much information do you actually need from the silencer to get that level of agreement? Are there some acoustic transfer functions that you have to put into the model? Or is it just the geometry, or what's the level of information you actually need to come to such an agreement?
Yes, very simple. Thanks for the question. Acoustics is complex, and a 1D model not always can capture all the details. But let's say if you limit the analysis to 1,000, 2,000 hertz, not more, you can capture the planar waves in the system, and you need detailed information about the length of the pipes and diameters, volumes, the location of perforations, and the size of the holes. And in this way, if you represent the internal structure with acoustically equivalent 1D piping systems, you can capture the transmission loss that is fully predicted. One issue is that if you have a transversal size, which is dominant, you will induce not only longitudinal waves, but also transversal. In this case, the transmission loss is completely different, and you need a 3D approach or a quasi 3D approach to capture the details. But until you limit your analysis to 1,000, 2,000 Hz, you probably capture all the information.
More questions? Yes, please.
Mauro Cateni from Caminois Italia. I wanted to ask you a bit more about how you are modeling the custom process inside the chamber in order to generate or if you support rate of release from experience.
Yeah.
What's the approach?
Yeah. Briefly, we can follow both approaches. I mean, we have different models. If you want, let me mention the diesel combustion, no premixed. We can have a double weave description, and we can introduce the rate of its release that has been measured. And in this way, of course, we get a good match between experimental and predictive pressure curve. Or we can use a more predictive approach in which we model the injection of fuel, the evolution of fuel, the air mixing and air entrainment, the air fuel ratio in different zones. So this is more predictive. And in this case, you calculate the rate of its release. The same for the premixed combustion model, where you have a two-zone approach, fresh gases, bird gases divided by a very thin layer. In this case, we can have the rate of its release imposed, and then you can use a two-zone model or Weber function, or we can follow a predictive approach in which we evaluate the turbulent flame speed from laminar to turbulent flame speed. In this case, you simply calculate to set the progress of the flame from propagation and calculate the rate of its release corresponding to this situation with emissions, with chemical composition and everything. So we have both approaches, simple but let's say useful for calibration or predictive.
Thank you very much.
Please.
It's Robert Zuiden from Anglo Belgian Corporation. I was wondering about combustion as well. Do you implement your own combustion strategy?
We are doing that. Of course, we implement our own combustion models and modes. So that's we can introduce different models. For example, we are working right now on RCCI, dual fuel combustion, and so on. So we have different routines, and eventually it is possible to give the opportunity to, to co-develop some approaches. For example, if a researcher, an engineer wishes to have a look and incorporate some special approaches, this is something that can be discussed because it's partly open. The solver, maybe the fluid dynamic solver itself is not of interest and it is not open, but some routines can be open. Yeah.
More questions? Okay, so a couple of information more. Before the picture, we are going to restart 50 minutes earlier than what we scheduled. So the afternoon session will start at 1:45. So please be sure that all the presenters from the afternoon have uploaded their presentations before 1:45, kindly. Okay, so and I can help. But now we make the group picture, and let's thank Angelo again. Okay, let's go this left side. My left side.
We stay on the stairs, but we stand up and we just make a big group. It's one.